We continue to learn Chapter 2, Determinants. Section 2, Properties of Determinants. So now we consider Part 2, Effects of row operations. First, we consider row operation 1, where two rows of A are interchanged. So A is a 2 by 2 matrix, and we write E to be type 1 elementary matrix. So we know that changing the two rows of A is equivalent to pre-multiplying A by E. So we consider determinant of EA. Determinant of EA just equal this 2 by 2 matrix. The first row is A21, A22. The second row is A11, A12 now. So using the definition of 2 by 2 matrix, we can easily get it equals A21 times A12 minus A22 times A11. And this value is the negative value of determinant of A. So if you use row operation 1, you get its determinant becomes its negative value. Okay, now for n greater than 2, let Eij be the elementary matrix that switches the row I and the row J of identity matrix. Okay, so for example, for this 3 by 3 matrix A, we use E13 times A. This means we interchange the first row and the third row of A. We get this matrix and we compute its determinant. And using the cofactor expansion along the second row of A of this matrix, we can get the determinant can be written in this way, which equals this one and also equals the minus the negative of determinant of A. So in general, now we consider n by n matrix A, and we let Eij be the n by n elementary matrix formed by interchanging the ith row and the jth row of identity matrix. Then we know the determinant of Eij. This means we do the row operation to interchange the ith row and the jth row of A. Its determinant just equals minus determinant of A. And in particular, if A is special, if A is the identity matrix, then we know determinant of Eij times I, which equals Eij itself. So determinant of Eij equals a minus determinant of this matrix A. A now is identity matrix, so it is minus 1. Thus, for any elementary matrix of type 1, we can get determinant of EA equals minus determinant of A, which equals determinant of E times determinant of A. So it's like the multiplication of these two matrices. Its determinant equals the multiplication of determinants. Now we consider row operation 2 considers a row of A that is multiplied by a non-zero scalar. Here, let us denote E to be the elementary matrix of type 2 formed from identity matrix by multiplying the ith row by the non-zero constant alpha. So we find the determinant of EA. We do its cofactor expansion along the ith row. We'll get this entry alpha times AI1 times its cofactor, just AI1, capital AI1, plus the entry here in the I2 entry of this E times A, just alpha times AI2 times its cofactor, capital AI2, plus TL plus alpha times AIN times its cofactor, capital AIN. So we can put alpha outside. We can get this one, this summation equals alpha times a term in the bracket. And the term in the bracket is AI1 times capital AI1 plus AI2 times its cofactor, capital AI2, plus TL plus AIN times its cofactor, capital AIN. just equals alpha times determinant of A. Okay, and in particular, if we set A, this general matrix A, to be identity matrix here, then we know that determinant of E, type 2 elementary matrix, just equals the determinant of E times I equals alpha times determinant of I. And for identity matrix, it's a diagonal matrix, right? Also special case of triangular matrix. So its determinant just equals the multiplication of diagonal entries equals 1. So we know determinant of E for the type 2 elementary matrix just equals alpha. And hence, we also have a determinant of EA equals alpha times determinant of A equals determinant of E times determinant of A. So for type 2 elementary matrix, its determinant EA, E times A is determinant, also equals the multiplication of these two determinant of two matrices equals a determinant of E times determinant of A. Now we consider the effect of row operation 3 on the determinant. Row operation 3 is a multiple of one row that is added to another row, and we obtain the new matrix. So let E denote the elementary matrix of type 3, formed from identity matrix by adding C times the ith row to the jth row. Expanded by cofactors along the jth row, we obtain that determinant of EA equals this number as AJ1 plus C times AI1 times the cofactor AJ1 plus this number times capital AJ2 plus TL plus this number AJN plus C times AIN times its cofactor capital AJN. And by simple computation, we can change this form to this form. This first n terms is just determinant of A, which equals the cofactor expansion along the jth row of A. And this term in the bracket, this one just equals 0 because it is AI1 times AJ1, where I does not equal to J. Plus TL plus AIN times AJN. By lemma 2.2.1, we know that this term equals 0. So determinant of EA just equals the determinant of A plus 0 equals determinant of A. Since E is triangular with determinants with diagonal elements all 1, we have determinant of E equals 1. Thus, determinant of E times A for the third type row operation. Third type elementary matrix, we know it equals determinant of E times determinant of A also. Now we make a summary for the effects of row operations on the determinants. So if E is an elementary matrix, then we know that for any type, type 1, 2, 3, determinant of EA equals the determinant of E times the determinant of A. Where if E is of type 1, we know determinant of E equals minus 1. If you change the two rows of the matrix, the determinant becomes its negative value, opposite sign. Okay, and if E is of type 2, we know that the determinant of E equals alpha, where alpha does not equal to 0. And if E is of type 3, so this row operation will not change the determinant of the matrix. So determinant of E just equals 1. And the similar result also holds for column operations. So if we post multiplying A by E, this means we do the column operation on the matrix A. Then determinant of AE equals determinant of AE transpose. This is the property we learned before. For matrix and its transpose, the determinants are the same. And for determinant of AE transpose, by the rule for compute AE transpose, before we learn it equals E transpose times A transpose. And the determinant of E transpose A transpose, because E transpose again is an elementary matrix. We know for any type of elementary matrices, its transpose is also an elementary matrix. So this one equals the determinant of E transpose times the determinant of A transpose. And again, using the property for two matrices which has a relation of transpose, its determinants keep the same. So it equals determinant of E times determinant of A. So again, for the column operation, you can also compute the multiplication of these two matrices. The latter one is elementary matrix. Its determinant equals the determinant of E times the determinant of A. Okay. Now, we also have these main results. The first one, all elementary matrices have non-zero determinants. Okay, so type 1 is -1, type 2 is alpha does not equal to 0, type 3 is 1. So all elementary matrices have non-zero determinants. If one row or column of a matrix is a multiple of another, the determinant of matrix must equal 0. So we also have this result. Because if one row of a matrix is a multiple of another, then you can use row operation 3 to transform this matrix with one row to be 0. Of course, because this type 3 row operation will not change the determinants of these two matrices. So if you have one matrix of one row entirely of zeros, this determinant must be 0.